Hi, I'm Denny, Marketing Manager here at the Hayes Bicycle Group, and I've got the new 2009 Manitou Dorado here. This is actually the final production version of the Dorado with our final graphics, and it's a fully functioning fork. It's new for 2009. We're going to be shipping them later this year. We're here in our Milwaukee facility where this is hand built, and I'm going to take you through the features of the fork as well as the internals and how it works.
Hey, I'm Dave Lee with the Hayes Bicycle Group. I'm your sponsorship event coordinator. I'm going to go over the external and internal features that the 2009 Dorado has to offer. We got your air side, where you're going to have your air in. Your air leg is going to come with air pressure rating between 90 and 50 psi. You got your air out, bottom of the fork. The air chamber is separated via a auto equalizing check valve. On the right side, blue cap is your rebound. Bottom of the fork is black. It's going to be your high-speed adjustment for your spawn bump sensitivity. Your red is your TPC plus for your square bump sensitivity, big hit. Also available in this leg is going to be your hydraulic bottom out circuit. Lasts 55 millimeters of travel. Won't blow your hands off the bars. Nice plush landing. The fork is comprised of a carbon fiber, a 2-ply custom weave. It's going to come in at 6.3, 6.4 pounds. It is 8 inches of travel stock, available to adjust to 180 mils, 7 inches. It has our patented hex lock axle, 20 mil, full bolt retaining. The crowns are unique. They are a hollow crown, which is a Manitou patent. It comes stock with 2 crowns. Got tall crown, big head tube. Flat crown, short head tube. Pretty simple. Along with your crowns, what will also come with it is 2 brake adapters. You're going to have your 8-inch post mount adapter, and you're going to have your 8-inch IS adapter. Development has been in place for the last 2 years. For 2008, we stuck out a handful of these on the World Cup circuit and were tested by Chris Kavorak for CRC, Matty Glycodin for MS Racing. So it has been through a year of World Cup racing. Stateside here, we've had a handful of riders. Team KHS, Melissa Buell, 4-cross world champion, rode for us, as well as her teammates got to sample, ride, and test the product for us.
I'm Ed Katersky, Engineering Manager for Manitou Suspension at Hayes Bicycle Group. I'm going to talk a little bit about the technology and the functionality of our Dorado downhill race fork. It's an upside-down fork, similar to what's common in the motocross world. At the bottom, starting at the bottom, we have our patented hex locked axle. It uses a hex shape to literally lock the axle to the dropout and tie those two together. So regardless of torsional loading, regardless of proper clamp loading, those two sides are locked together. We have 2 bolts per side, providing a clamping load to that axle. It is the 20 millimeter standard. We have forged dropouts that are pressed and bonded to the aluminum slider legs. We have a 36 millimeter male slider leg. It's made of extruded drawn aluminum. Coming up here to the seal sleeve, this is bonded to the carbon upper tube. The carbon runs from the seal sleeve up to the upper sleeve, one continuous piece. That's a dual wrap high modulus carbon. The 3 sleeves are bonded with carbon epoxy. In the seal sleeve, we have a motocross style oil seal inside. And these are generally capable of holding around 1500 psi max. And then we have a dust wiper, which in the bicycle industry, a lot of forks use just a dust wiper, and they're capable of holding in low pressure, but they're really designed to keep dirt out. By using a dual seal system, we are able to use an open bath and well lubricated fork and really provide a reliable leak-free seal. It's an air-sprung fork. We've gotten around many of the problems with the air systems that historically prevailed by designing the fork to have a very linear system through the use of a large volume. The spring chamber is actually in the lower part of the fork leg here, and that provides excellent heat transfer to the atmosphere to reduce the thermal effects, expansion of the air. The air piston is on the end of a rod, which attaches that ties in the top of the fork to the lower end of the fork via the end cap, which threads to the lower fork. The piston, the air piston, has a PTFE or Teflon piston band, an orange seal, and a check valve. The fill process for this fork, you put air in the top fitting, and that air goes down the hollow rod, filling the negative chamber and the positive chamber, extending the fork, and when these are extended, both sides of the piston are in equal pressure. That provides for soft top-out force. Once the fork compresses, you build pressure on the positive side of the piston. Pressure on this side reduces. Check valve provides a fail-safe to make sure that any loss of pressure across the seal can rebalance. There's also a spring chamber generated in the design between this cap, the end cap of the fork, on the lower leg and the top cap on the upper leg. So as you compress, you're actually generating a spring load in this chamber. That provides some redundancy and some fail-safe capability. And it also causes the fork to always drive back to full extension, even if you're actuating your check valve. We've done thermal optimization through some research on the clearances and the heat buildup, causes of that heat buildup, and have reduced the effects of heating throughout your ride, your downhill run. When the rider wants to reduce air pressure, unscrew the bottom cap and you bleed the pressure out the bottom. What that does is that bleeds out the positive chamber, and the negative chamber is going to follow through the check valve. If you bleed off the top side, the check valve prevents air from leaving the positive chamber. So you're not going to achieve your goal of reducing air pressure if you were to follow that. So technique and following instructions is very critical on this fork. Going over to the damping side, we have a dual adjust compression circuit, and this utilizes our energy-dependent TPC plus circuit, which is a piston that moves and responds to the travel and the velocity that your fork is seeing. So what that does is allows, at a lower velocity of long travel situation, it maintains a lighter damping force, but on a big hit, severe impact situation, it engages an additional circuit, generating a high energy absorbing damping situation. Again, that's in the bottom of the fork. The red knob adjusts the tapered needle. Now in this system, that tapered needle, while it does affect low speed damping force, has a greater effect on the engagement timing and engagement force of the TPC plus circuit. That's really going to be used for your adjusting your big hit situations, how much travel you want to see, you want the fork to absorb on a bump landing, for example, or striking a severe bump. The outside collar here adjusts a traditional high-speed circuit, which you see here with the coil spring applying a preload to a second piston, which is buried in the sleeve here. So as this system is really a pressure-sensitive system, in that the hydraulic pressure generates a force against that shim stack and against the coil spring. And when that pressure rises enough to exceed the preload on your spring, it'll open and activate that circuit. before those systems, before your TPC Plus system and your high-speed system engage, the low-speed flow is actually going through the center of this needle, and it has a choice. It can come out across hole and go through the high-speed circuit, or it can continue on through the tapered needle and out through the orifice, which is created with the adjustment position of the red knob. What that's really doing is controlling the oil that bypasses the TPC Plus circuit. So by tightening up your tapered needle, you can force more oil to displace and engage your TPC Plus, creating a lot more energy absorption capability, so you won't blow through the travel should you adjust it that way. When it's wide open, most of the oil is going to go through the center circuit, bypassing this, allowing the fork to use its full travel without generating any pressure spikes or compression spikes. So you can run that system very plush and utilize your full travel and still have excellent bottom out control, because this whole system, this is your compression system, sits in here. That's all velocity and energy dependent. We have a hydraulic bottom out system which is primarily position sensitive. So when you get down near full travel, you engage a bottom out circuit, which is it's a cup here. It's full of oil, and the oil is going to sit up to about this level in the fork. And as it travels, as the fork compresses, that oil level climbs a little bit due to the rod volume displacement, and your bottom out plunger will engage that cup about 55 millimeters before bottom out, and now the oil has to squeeze through the diametral clearance between the plunger and your cup. And there's another picture here. It's showing the circuitry inside the aluminum sleeve. We have a series of small orifices that add some further position sensitivity to the system. As you compress, you get in your bottom out, rather than having a painful bottoming event, you absorb a tremendous amount of energy through the hydraulic resistance of this motion. So you clear some oil out past the diameter and up through this series of small holes. So as you compress deeper and deeper, these holes close off until you have, at the very end, you have one small hole and a small clearance around the diameter of your plunger, so that damping force ramps up tremendously, and in the vast majority of situations will prevent a physical bottom out of the fork. Even then, on the spring leg, we have a rubber bumper, so that there's never any metallic hard contact. Should you blow through your hydraulic circuit, at the very end of travel, you have 5 to 10 millimeters of compression of your rubber bump stop. On the opposite side of that system, you have a rubber top out. So providing a soft, gentle transition at both ends of your stroke, not just focusing on the mid-stroke and the bump absorption, but how the suspension changes and comes to a stop at both ends of travel is very critical to ride quality. Integrated into the same subassembly as your top-out system is your rebound circuit. It uses a traditional piston and bending shim stack. Inside here is a tapered needle. That tapered needle position and that flow path is adjusted with the rebound knob on top of the fork. It's pretty straightforward technology. It's used in the vast majority of cartridge forks. It's very sensitive to stroke velocity. The low speed, most of the low speed flow is going to go through that tapered needle. So if you really want good small bump compliance, you run that tapered needle open a little bit so that the wheel can always follow the ground. When you're coming off of a big landing where you've really loaded up your springs, now you're gonna unload those springs, and you want to prevent that bicycle from rebounding, kicking you off the pedals, or or bouncing off the ground again, that's a higher velocity event, and that's gonna force oil through the shim stack. And that's, we've optimized that for the majority of grinders. It is further adjustable. You can send the fork back to Manitou, have that custom tuned. A knowledgeable suspension tuner can do that on their own. And the same thing with the compression circuit. There's a myriad of changes that could occur inside here should you be completely unable to tune it in with external adjustments. Now, for the rider who's struggling with that setup, we're going to have the ability for them to contact Hayes and work with somebody here to tune that in correctly. We'll have a tuning video and forums on our website to help people out, and really offer the end user an infinite amount of tunability and support to achieve it. Another interesting feature of the compression of the damping circuit is we are able to separate our air column from our fluid column without the use of an internal floating piston. Traditionally, an internal floating piston, or IFP, is used to provide a physical barrier between the air and the oil to prevent aeration of that fluid column. Aeration causes inconsistent damping force, as you essentially are pushing air bubbles through the damping circuit, which is not going to give the same response as pushing a liquid through there. And also, an aerated fluid column has some compliance. So instead of pumping oil, you're actually just compressing the fluid column. We use nested tubes. The inner tube, which is where the damping oil is housed, is the same diameter as our cross-country and trail MRD forks, the Minute MRD and the R7 MRD. This is nested inside a larger tube, and there's a space created between the tubes, and these are inside the cartridge. So what happens is, when compression flow goes through the compression circuitry, it'll come out of the piston and go into the space between the cartridges. That creates a long barrier of oil between your damping circuitry and your air column. It comes up to the top through some small holes to the area above the cartridge, and it sits up here. This provides a pool of oil for your bond mount circuit to function, and also it provides a direct transfer medium between the fluid column and the aluminum structural leg. So that allows the heat dissipation to occur to the atmosphere rather than being completely insulated with an air sleeve. Now, the agitation that aerates your fluid column occurs up here at the boundary between the fluid and the air. For any aeration to get into your damping circuit, it now has to go all the way down the leg, through the valving, and into the slender inner chamber. Very unlikely to occur.